OK. So I want to just, in the remaining few minutes, get started on something else that I'd like to talk about, which is related to the question that we left aside, and that is, what about alpha S corrections? And there's a couple of things here that are interesting. But basically, it boils down to, we've already seen how to do matching and renormalization group in evolution. But now we have these extra labels. And so we can ask, what impact does having labels on that whole story of matching and renormalization group evolution, what impact does it have? And we'll say that there are examples where it does have an impact. So HQET radiative corrections. So if you like, we're just thinking about the renormalization, as we should for any effective theory. Think about what's the renormalization structure. And since it's a top-down, we can also think about matching. So we should think about renormalization of L. We should think about renormalization of external currents, like the ones we were talking about over there. And if we match a full theory current, the way that you should think about what's happening from matching is that there'll be some Wilson coefficient that's generated by radiative corrections. So once we think about adding alpha S corrections to our story, there could be radiative corrections in Lagrangians. We'll talk about that. But there also are non-trivial radiative corrections here in the currents, where they get multiplied by something that depends on virtual interactions having to do with antiparticles that we're integrating out. That just affects these currents, the current relations, by multiplying them by some coefficients. Yeah. So the first thing that actually differs, and it's because, again, there's no antiparticles, that changes the nature of loop diagrams, is the wave function normalization. So we have to go through that again. So if we do field renormalization, it's the same kind of story as it is in QCD. We have to consider this diagram, but we have to calculate it now in HQET. So let there be some external, I'll call it P. I should call it K. Call it K. There'll be some loop momentum. We have Q plus K. If we use dimensional regularization, then this loop integral looks like this. So using MS bar, there's some usual MS bar type factors. And then there's the relativistic propagator, which I'm using Feynman gauge, so it's just Q squared. And then there's the heavy quark propagator, which would look like that. So the loop integral that I have to do here wouldn't have two relativistic propagators. It has one heavy quark propagator and one relativistic propagator, and it will give something different. And we'll talk about it in more detail next time, about evaluating this loop integral. So I wanted to do one loop integral for you. And basically the way I'm going to talk about the renormalizations and matching is I'll do this loop integral for you so you have some idea what would be involved if I was asking you to do them yourself, which I don't think I'm going to do. And then I'll just be quoting results for you and telling you kind of how the structure of the theory looks, and where the corrections are going, and talking about more the important things that come out of the results rather than dwelling on calculational details. But we will talk about one calculation, because there's one trick that you should know if you ever encounter an integral of this type, since it's different than just using a Feynman parameter trick. And that difference comes about because this guy's linear in the loop momentum, this guy's quadratic. You have to know how to deal with that. We know how to do matching and running. We've seen an example of that. In this theory, there's this label V on the fields, and we want to figure out how that affects doing matching and running. So we started out talking about the wave function renormalization calculation. So we have these fields which we can have a bare version of and a renormalized version of in the usual way. So this is renormalized and this is bare. Some z factor between them that I'll call zh for z heavy. And so we have to calculate at lowest order this diagram. Send in a momentum p. This is q plus p. Use the Feynman rules. Use dimensional regularization. Use dimensional regularization with MS bar. So there's some extra factors. And use Feynman gauge, which is usually the simplest gauge choice. So each of these vertices here gives a v. There's a v mu from this vertex, a v mu from that vertex. And that's where this v squared comes from. And then there's one propagator here. It's very traditional to denote a heavy quark by 2 lines rather than 1 line, so you know which lines are heavy and which lines are light. So these 2 lines is a heavy quark, and that gives this propagator here, this v dot q plus p. And then there's a relativistic propagator for the gluon. That's the q squared. I've taken into account all the i's when I put this minus sign, and this is just the fundamental Casimir from dotting 2 TAs together. OK. So when you have an integral like this, so v squared is 1. That's one simplification. When you have an integral like that, where you have a linear momentum in one propagator and a quadratic momentum in the other propagator, you don't want to use the standard Feynman trick. I call this trick the Georgide trick. So it's very similar to the Feynman trick, but slightly different. So you use an integral that goes from 0 to infinity, and you can convince yourself that this is true. And so then set a equal to q squared and b equal to v dot q plus p. And the reason that you want to use this trick rather than the usual one is that if you use the usual one, you'd get an x multiplying this and a 1 minus x multiplying that. But then you would have an x multiplying the q squared. So when you complete this, it would be, when you want to complete the square, you'd like nothing to multiply the q squared. You'd like the q squared just to be bare by itself with no Feynman parameter multiplying it. And this trick does that because a has no Feynman parameter multiplying it, or Georgide parameter in this case. OK, so we combine denominators. And the usual way. And the denominator would become this, and if I kept the I epsilon, it would be that if we combine these 2 denominators here. So this factor would be that. And we can then complete the square and write this as some momentum squared minus whatever's left over, where t is q plus lambda v, and then a. It's the rest of the stuff, which is this. OK, so then this guy. Now we just have a usual quadratic integral that we can use the standard rules to do. And then instead of an integral over x, we have this integral over lambda. There's some factors that I'm dropping. there's that e of the Euler gamma times epsilon and the 4 pi to the minus epsilon. So write in everything with d equals 4 minus 2 epsilon. Do that integral, which is just giving some gamma functions. And if you think about the dimensions here, so we end up with something that's d minus 3. If you want to look at the dimensions, d over 2 minus 2 is dimensionless. Okay? The lambda had dimensions. If we go back here, that's obvious. Q is dimensionful, v is dimensionless, so lambda has dimension 1. So the dimensions of the mu to the 2 epsilon are compensating the dimensions here. And then there's 1 power of dimension left, and that's why if I take d equals 4, I'm getting 1 power of momentum upstairs, which is what we'd expect for an inverse propagator for a heavy quark, is 1 factor of v dot p. So expand this. And we get a divergence. So add a counter term for wave function normalization. So if we did that in MS bar, then the ZH would be just this. And that would be the appropriate counter term to kill off the 1 over epsilon divergence. I'm going to carry out the calculation today, or this discussion of matching in MS bar for everything. And I'll show you that there's a slight complication that shows up in that case. But we said that we could do matching. Basically, you could have 2 choices here. You could either use on-shell renormalization, or you could use MS bar. What's the difference? In MS bar, you just keep the divergence in the z. In on-shell renormalization, you keep some extra terms here. All right? And either way that we choose to do things, we should actually end up with the same matching. And I want to show you why that's true. So in order to show you why that's true, I'll pick to use MS bar at this point, and we'll see what complication that leads to later on. OK, so that's one thing that needs to be renormalized. And if we look at this guy and we compare it to z psi, this is not the same as z psi in QCD. So this is something different, and the reason it's different is because we did a different loop integral, had this heavy quark propagator, not the light quark propagator. So we have to renormalize also local operators. And so let's think about something that would make a heavy to light transition. So for example, if you looked at B goes to U, electron, neutrino, then that would be a heavy to light transition. The B quark is heavy, the U quark is light. So to describe that, you would use some operator that has 1 heavy quark and 1 light quark. So let me call the light quark small q, and the heavy quark big Q. And so you'd have some operator that looks like that. And we could write down a renormalized operator. With renormalized fields, and then group all the z factors into a counter term. So let's think about doing the perturbation theory that way. So this is the renormalized operator. This is the counter term. So there's a wave function factor ZQ for the light quark, a ZH for the heavy quark, and then there's some ZO for the operator renormalization. OK, so to renormalize this operator at one loop, we insert it, And we do a one-loop diagram. I'm just going to tell you the answers. So let's draw the diagram. So here's the operator inserted. Here's your heavy quark. Here's your light quark. You have a diagram like that. And then you combine this calculation with the wave function renormalization, ZH and ZQ. ZQ is the same as Z psi. We should have called this ZQ for a light quark. Combine these things together, and then because that graph is telling you this counter term, you need ZO. And that calculation, which you can look at in your reading if you want to look at more details, just gives you kind of something about what you'd expect. It gives you a 1 over epsilon divergence, factor of g squared. So the operator here has a renormalization. It's just minus alpha s over pi. That's the anomalous dimension. So what is this anomalous dimension doing? It's, if you were to consider this kind of process in full QCD, then you'd have here gamma mu, 1 minus gamma 5, and that's a partially conserved current. So there would be actually no anomalous dimension to this operator. The vertex graph that we just drew over there would cancel the wave function graphs exactly. There'd be no anomalous dimension. But here we have one. And that's because these guys are not equivalent anymore. You saw that the Z for the heavy quark changed, and the vertex graph also changes, and we're left with something. And this remainder has to do with renormalization group evolution below the mass of the heavy quark. Above the mass of the heavy quark, there's no renormalization group evolution of this current. Below the mass of the heavy quark, there is. So there's additional logs, and that's because MQ is now being treated as infinite. So things that, from the point of view of QCD, were logs of MQ, have now become UV divergences, and that gives an extra anomalous dimension. One thing you can note about this anomalous dimension is that I didn't really specify for you what the gamma was, although I told you for this process it would be gamma mu 1 minus gamma 5. And the result here actually, if you carry out this calculation with arbitrary gamma, you find that it's independent of gamma. So you get the same universal anomalous dimension for any spin structure. And that's partly related to the things that we talked about last time with the spin symmetry of HQET, which is telling you that certain couplings are not sensitive to the spin. And effectively in this diagram, you're getting a V slash here. Well, let me not try to go through it, but leave it for looking at your reading. But we'll talk a little bit more about this in a minute. I won't try to explain where that comes from the diagram. So let's look at another case. The only real interesting thing that happened here was that we got, well, the fact that the answer was non-zero was interesting, and the fact that it was independent of gamma. But the V didn't show up. And the reason that the V didn't show up in this calculation here is because there was only one V, and V squared was equal to 1. So V couldn't really show up because we had to get a scalar answer. And since V squared is equal to 1, it's not showing up. So something more interesting is to look at, instead of a heavy to light transition like that, a heavy to heavy transition. So we'll spend a little bit more time on this one. So let's have two heavy fields. And I'm going to take them in a current where they have different velocities, v and v prime. So let me imagine I went through this procedure of separating out counter term and normalized operator, just like I did over there. So I have these two terms, two types of structures. Now I don't have a ZQ, but I have two heavy quarks, so I have ZH, root ZH, which is just ZH. So an example of this would be something like a B meson changing to, say, a D star meson, an electron, and a neutrino. So having a charm quark replace our up quark. Okay, so now the charm quark and the B quark could both be thought of as heavy. They have different masses, but we take both of those masses to infinity, so we can use HQET for both of them. So MB and MC are going to infinity. And there's no reason why in this process that the B quark and the charm quark should have the same velocity. And so we'll give them different velocities, v and v prime. OK, so we can go through the same thing. We already calculated ZH, so we just have to calculate a graph like this, where we have two heavy quarks, but the heavy quarks have different velocities. So what would that calculation look like? Again, in Feynman gauge. And let me just take the external quarks to have zero momentum for simplicity, zero residual momentum. So this guy has like k equals 0, k equals 0. So the HQT Feynman rule for this guy has a v dot q, if q is the loop momenta, and this guy has a v prime dot q. Okay, so the integral that I have to do is that integral. And you can do this, again, with one of these tricks with like where you use lambda parameters. And on one of the handouts on the web page, I've given you the appropriate trick with 2 lambda parameters for this integral. This integral actually has both ultraviolet and infrared divergences. We're here in our discussion only interested in the ultraviolet ones, because we're worrying about the anomalous dimension right now. And again, I'm not going to drag you through the details of this calculation. It's essentially just do the Feynman parameter, combine denominators with 2 Feynman parameters, complete the square, do the loop integral, do the Feynman parameter integrals, get an answer. Combine it together with the counter terms for the wave function or normalization, and see what type of counter term you get left over. And it's more interesting than the heavy to light case. So here's what it looks like. Where W is v dot v prime, and this function r of w is the following. It's log w plus square root w squared minus 1 over the square root of w squared minus 1. Okay, so it's kind of a non-trivial structure. So that counter term would lead to an anomalous dimension, which depends on this r of w. So the reason that can happen is because v squared is 1, v prime squared is 1, but v dot v prime need not be 1. So v squared was 1. V prime squared was 1, but v dot v prime is not fixed. Well, it's not fixed simply by poor choice of words. This is a parameter that can vary. So it will be fixed by kinematics, but it can depend on the kinematics. So let me go through this and organize it as a bunch of notes, comments. So this is what I just said, that it depends on, the answer depends on v dot v prime. And the way that you should think about this is that you have a current in the effective theory. So this is in the HQET current. And just like we label it by its Lorentz index mu, we should label it also by the v and the v prime, because the fields involve v and v prime. So if we thought of this as some vector current or axial vector current labeled by mu, we would also label the current by v and v prime. So these are indices that are just indices on the current, and when you think about the Wilson coefficient or the anomalous dimension, it can depend on those indices. Now, because the Wilson coefficient is a scalar, it really only depends on W. So if you think about Wilson coefficients, they depend on alpha s, they depend on scale, mu, they depend on the hard scales in your problem. And the hard scales in the problem here for us are mb times v and mc times v prime, because those are the heavy scales of the heavy charm quark and the heavy B quark that we're removing. But since we know that this thing is a scalar, we can just square these, dot them into each other. So it's really a function of mu, of alpha s mu mb squared from squaring the mb term, and charm squared, and then this w factor. Those are the scalar quantities it can depend on. So what should I take for the w? Well, we can work that out for an example like the one I was saying that we're doing, like b to d star L nu. So let me show you how that works. So for the B meson, for momentum, we can take it to be m capital B meson times v mu. And by momentum conservation, that's going to be the d star momentum, which we can take to be m d star times v prime mu, and then some momentum transfer, which I call q. This is a different q than my loop momentum q. Sorry about that. So then we can just take this relation and we can square it, and we can get v dot v prime. So if you look at q squared, you can solve this for v dot v prime, and it's just fixed. You see that v dot v prime is fixed in terms of the meson masses and the momentum transfer, and that's the momentum transfer to the leptons here. How much momentum do they carry away? So you could think of all those things as external. You fix how much momentum the leptons carry away. These are fixed numbers. You look them up in the PDG, and then you know what value of v dot v prime to plug in here. Now it's a function of q squared. Q squared can vary in the process. So in that sense, it's a non-trivial function, not just a fixed number. But for any fixed kinematic configuration, any fixed q, then it would just be a number. So if you look at this in practice, you find that this guy, for this particular case, goes from 1 to 1.5. So that's the kinematic range that's allowed. So it is fixed by external kinematics, kinematics that is external to the dynamics inside the loop. And in that way, the Wilson coefficient here is more non-trivial than the ones we saw earlier, which just depended on masses. Now it's depending on masses as well as this function of v dot v prime. Okay? Again, one finds that this gamma t comes out to be exactly the same, independent of the choice of the spin structure. So we could do this calculation with any spin structure we like, and heavy quark symmetry in this case is all it takes to show that this gamma t is independent of the spin structure. So if you think about that from the loop graph, actually in this case it's pretty easy to see, because remember that this vertex didn't have any spin structure, the propagator had no spin structure, so nothing in the calculation had spin structure. So the only thing that had spin structure is the gamma you stuck in there. So it's just a scalar times gamma, so it doesn't care about the gamma. Whatever the tree level gamma is, it just goes through. It's not touched by heavy quark, by the HQET Lagrangian. So what is physically going on here, and what is the HQET doing for you, is that there's logs like this, mq over lambda QCD in QCD. And by going over to HQET, this becomes a log of mu over lambda QCD, which is encoded in HQET operators, like this current, as well as a log of mu over mq, or mq over mu, which is in the HQET coefficient functions, HQET Wilson coefficients. So just how much exactly the same as how we talked about it for integrating out a heavy particle, the logs get split up into pieces in the Wilson coefficient, pieces in the matrix elements, operators. Here we're separating MQ, heavy quark mass. And it's both the charm and the bottom in the case of that we're talking about. And the anomalous dimension that we calculated sums up those logs, and summing up those logs involves a non-trivial function of this W. But we actually know exactly the non-trivial function because we can calculate it. And it's just this guy here. Okay, so the new wrinkle that can come in HQET is that the anomalous dimension can become a more non-trivial thing. So if you look at it at leading log order, the rest is kind of pretty straightforward. So if you go through the leading log result, you would do the same type of thing that we did before. You would match it some scale. And at that scale, you can normalize things so that the Wilson coefficient at mu equals mq is just 1 at tree level. And then the leading log result is a function of these various things, which in general is c of mq times some evolution from mq to mu, suppressing some of the dependencies. The leading log result is 1 for this. And then this guy at lowest order is just a ratio of alphas again. And then there's the gamma, for the purpose of solving the RG, is just the only thing that matters is its alpha. So gamma is a constant for heavy to light, just a number. For that current, is a constant. The solution is actually valid for both of them. And then it's a function of this W for the current, where we have two heavy quarks. So the W dependence just goes along for the ride when you're solving the enormous dimension equation. Okay, so that's what resumming the logs would look like. Essentially, each log is getting extra powers of this factor of gamma. So that was number 4. So any questions about that? Okay, pretty straightforward. So much of this, essentially all of the story except for this little wrinkle is very similar to integrating out a massive particle. And the other part of the story that's similar is that the HQET matrix elements depend on mu as well. And so in our example that we talked about last time, we had a matrix element. So let me give it to you in the context of that example. So last time we were talking about something which was a decay constant. And that's one example of this heavy to light current. So we had a current which had one heavy quark, one light quark, and then a heavy meson. And we figured out that this was giving some A times V mu. And now I'm telling you that you should think of the A as a function of mu. The matrix element here is a function of mu. Okay, so that's just a slight modification to what we talked about last time. And again, if you want, for this matrix element, you want mu to be, say, a GV or some scale that's greater than lambda QCD. And so what you would do is you would evaluate matrix elements and define that parameter at some scale like a GeV and do renormalization group evolution from the heavy quark mass down to a GeV. Okay, so that's how the renormalization group evolution story would be. You don't want to run all the way down to lambda QCD because the enormous dimension has to remain perturbative. So you decide what your cutoff is for where you think perturbation theory is still valid. And often people pick something like 1 GeV or 1.5 GeV for these types of problems. And again, this is just separating out all the MQs, making sure that your matrix element here has no MQs. It does have an extra cutoff mu. Okay. So that's the RGE story.